In this video, we're going to talk about the dual solution, the dual problem. The primal problem is the original problem that's actually solved by the simplex method. We're trying to maximize a linear function of x with equality constraints. Remember, the simplex method requires equality constraints. If you have greater than or equal to or less than or equal to constraints, you have to convert them to equalities by adding or subtracting slack variables. And then you always have to have zero lower bounds on all the variables, normal or slack variables. The dual is this problem here. Dual problem is minimize, notice not maximize, but minimize B transpose Y with A transpose Y greater or equal to C. Notice the roles of C and B have been switched here. In the primal problem, B is the right-hand side vector. Here it's the coefficients of the objective function, and C is now the right-hand side. But this is sometimes called the non-symmetric primal dual pair because symmetry not referring to the matrix A, but to the fact that there's no symmetry here. You switch the roles of B and C, but on the other hand, you have lower bounds on X but not on Y, and you have greater than or equal to rather than equal to. In a moment, we'll see something called the symmetric primal dual pair, where there's complete symmetry, everything's switched. Okay, the dual problem is related to the primal problem very closely. First of all, it's easy to prove that B transpose Y for any dual feasible Y is greater than or equal to C dotted with X for all primal feasible X. In other words, if you take any Y which qualifies as a feasible point for the dual and calculate the objective function, and you take any X that qualifies as a feasible point for the primal problem and calculate the objective function at that point, the D is bigger than the P. That is, all values of B transpose Y are greater than all values of C transpose X. That's easy to prove here. B transpose Y for any dual feasible Y is equal to AX transpose Y because B is equal to AX if X is primal feasible. That's equal to X transpose A transpose Y, and then if Y is dual feasible, A transpose Y is greater than or equal to C, and X is greater than or equal to 0. Notice the fact that A transpose Y is greater than or equal to C does not automatically make this true unless the components of X are also greater than or equal to 0, which they are. So that proves that all values of D are bigger than all values of P. That means the minimum of D is greater than or equal to the maximum of P. Now we'll see in a minute that they're actually equal, and the vector Y, the dual feasible vector Y, which makes D equal to P, is the solution of the dual problem, and the X that makes P equal to D is the solution of the primal problem. So all P's are less than all D's, therefore the minimum of D is greater than or equal to the maximum of P, and that we've proven easily. We're going to show in a minute that they're actually equal. So, in fact, the solution of the dual problem is the same as the solution of the primal problem. That is, the maximum objective function of the primal problem is the same as the minimum objective function of the dual problem. That doesn't mean that X and Y are the same. In fact, they're not even the same length. X is an n vector and Y is an m vector, but the minimum of D is equal to the maximum of P. So far, all we've proven is that the minimum of D is greater than or equal to the maximum P, which, by the way, proves something else. It means that if the primal problem has an infinite maximum, then the dual problem has no feasible solution, and vice versa. The dual problem has an unbounded minimum, the primal problem is infeasible, because if the dual problem had any feasible solutions at all, then B dotted with that Y, that dual feasible Y would be an upper bound for the primal problem, and therefore it couldn't be infinite, and similarly the other way. So if one problem has unbounded maximum, the other has no feasible points, and vice versa. It's a little too detailed to go into in the audio here, the proof that the primal solution is equal to the dual solution. It's in the book, but let me make a few comments about the proof. First of all, let's suppose that we run the simplex method on a problem with artificial variables, and we finish it, and now we know which variables are in the final basis. Then let's go back to the initial simplex tableau and start all over, but this time let's switch the columns so that the variables that we know are going to end up in the final basis are all listed after the variables that are not in the final basis. So here's the initial simplex tableau, but we have ordered all variables that are going to be ultimately in the final basis. Of course, we're not going to know this until we've solved the problem once, but say we solved it once and we know then which variables are going to be in the final basis. And in fact, that's the whole point of the simplex method, is finding out which variables are in the final basis. Once we know that, you just set the others to 0 and solve for those, and you're finished. So let's say somehow, because we've solved it before or whatever, we know which variables are going to end up in the final basis. So we write the initial simplex tableau. Remember, this is the initial simplex tableau. And the first, the columns corresponding to the non-basis variables, the ones that are ultimately going to be set to 0, are listed before the ones that are set that are going to be in the corresponding to the ones in the final that are in the final basis. So A sub B are the columns of the original A. Now this is actually part of A, but it's the columns of A that correspond to the variables that are going to be in the final basis. A sub B. Now, if we knew that, then all we'd have to do is solve for those, and in fact, this is what the final simplex tableau will look like. We have an identity in the columns corresponding to the final variables in the final basis, and we'll set these other variables to 0, solve for those, and in fact we'll get the solution will be AB inverse B. So in other words, if we knew somehow which variable is going to be in the final basis, all you have to do is take those columns, put them into a square matrix, M by M square matrix A sub B, and solve A sub B x equals B, and in other words you get the final solution is x equals to A sub B inverse B. Those are the basis variables. The others are going to be 0. So your final solution is basically A sub B inverse B. Now the theorem 432, which we're not going to go through the entire proof, but it's you can go through it on your own, says that the dual solution y star is AB minus transpose CB, AB being the M by M matrix, the portion of A corresponding to the variables that are in the final basis. So you take A sub B minus transpose times C sub B, C sub B being the portion of the C vector corresponding to the basis variables in the final basis. Then y star is going to be the dual solution, and we just said that AB inverse B is going to be the non-zero part of the primal solution. So basically, to prove this theorem, what you have to do is show that this y star is primal feasible, dual feasible, and we'll show that B dotted with y star with this dual solution is actually equal to P max. So remember, we said that B transpose y is greater than or equal to X transpose C for all dual feasible y and all primal feasible X. And if we can find one X and one y such that they're equal, then you found the minimum of the primal and the minimum of the dual and the maximum of the primal. So the proof basically consists of showing that this y star is the y which makes B transpose y star equal to C transpose X, where X is the solution of the primal problem. One other thing I'd like to point out is that in the final simplex tableau, we can actually find the dual solution hidden there in the last row. The primal solution is this, AB inverse B, so all you have to do is look on the right-hand side and you've got the non-zero portion of the primal solution. The dual solution is actually going to be down here in the last row in the columns corresponding to the artificial variables. So remember, y star is AB minus transpose CB, so y star transpose is exactly this thing here. The point is, once you have solved the primal problem, the dual basically is just sitting there for you. So we don't actually have to go back and solve the dual separately. We don't have to do any extra work at all. Once we get to the final tableau, we can read the primal and the dual solution off. Okay, now let's talk about the symmetric primal dual pair. If we have a resource allocation problem, you know we have less than or equal to constraints, not equality constraints, and we have to add slack variables before we can apply the simplex method. So let's look at our resource allocation problem where you have the less than or equal to constraints, and let's see what its dual is. And to find its dual, we have to first add the slack variables to convert it to the form that the simplex method solves, and then look at what the dual of that is, and that's what we're going to do now. So we add the slack variables onto the end of our x vector. S is the vector of slack variables, and it has 0 coefficients in the objective function. And then we have this identity here times the slack variables, and there's our equality constraints after adding the slack variables, and we still have bounds that both the normal variables, the regular variables, and the slack variables have to be greater or equal 0. So now it's in the form that the simplex method can handle, and we know what the dual of that problem is. The dual of that problem is this, minimize B transpose Y with, and this is our A transpose. It's the transpose of this matrix here that includes the slack variables. Take the transpose of that, we get that greater or equal to C, but now C, remember, includes the slack variable coefficients. But this, if you write it out, translates into A transpose Y greater or equal C and Y greater or equal to 0. So now we have what we call the symmetric primal dual problem, because here's the dual of our resource allocation problem, and it's symmetric in the sense that we switch minimize and maximize, we switch the roles of B and C, we've transposed A, and the constraints were less than or equal to, now they're greater or equal, so everything is just reversed. And we do have bounds on the Y, so this is basically a blending problem. The dual of a resource allocation problem is a blending problem where you're minimizing something with greater or equal to constraints and bounds of 0. So our resource allocation primal problem then has as its dual this blending problem. B and C have been switched, maximize is changed to minimize, A has been transposed, less than or equal has been changed to greater or equal, but we still have lower bounds, greater or equal 0 for both X and Y in the primal and dual. Okay, now you're no doubt asking, what good is the dual problem? Why do we care about the dual problem and the dual solution? Well, there's about 3 things at least that the dual is good for. One is simply sometimes the dual problem is easier to solve than the primal because of the dimensions of the matrix. That's not so important usually. Secondly is that in problems such as your homework problems 4.3 and 4.4, you have linear programming problems that have no lower bounds. In other words, your variables are not required to be greater or equal 0. They may in fact be negative, and that can't be solved by the simplex method directly. However, if you can write that as a dual problem, and you can in problems 4.3 and 4.4, then you simply solve the primal problem, which can be solved by the simplex method. That's the second purpose of the dual. The most important purpose of the dual is the physical interpretation of it. Remember that we proved that if y star is the dual solution, that is, it's the dual feasible y which minimizes d, then b transpose y is equal to p maximum, is equal to the maximum of the original function. So the maximum of your original objective function, your primal problem, is equal to b transpose y star, which means b1 y1 star plus etc. bm ym star. Now, what happens if you change one component of b a little bit? Well, if you change it a small amount, small enough so that the final basis does not change, which means that y star isn't going to change because it's just a sub b minus transpose c sub b, and if the basis doesn't change, a, b, and c, b are exactly the same. Those are the a and the c and the original a and c, the columns of a and the columns of c, the elements of C corresponding to the final basis. So if you don't change the final basis, the dual solution doesn't change at all. That means that the P max will change how much? Well, if the dual solution doesn't change at all and you only change one B, then the amount of change of P max will simply be Y sub j times the change in B sub j. Okay, to give you an example then of the use of the dual problem, let's go back to our chair table factory, our furniture factory, our resource allocation problem. And we solved that earlier in a previous video. It's solved in section 4.4. We were trying to maximize our profit, figure out how many chairs and tables per day we should produce to maximize our profit with limits on resources. We had a certain limit on the number of man hours, machine hours, and wood that we had available. We solved the primal problem with the problem using the simplex method, and we found out that we should produce 12 chairs and 18 tables, and that would give us a profit of $1,380. That's the solution. Now, what is the dual problem good for? Well, the dual problem, as I said, is just sitting there in the final tableau to be read off in the columns in the last row underneath the artificial variable columns. And it turns out to be 18.33303.333. What does that mean? That means that the fact that y1 well, let's say the fact that y3 is 3.3 1/3 means that if we change the limits on B3, if we increase B3 by 1 unit, assuming that's not big enough to cause a change in the basis, then our profit will increase by $3 1/3. So the dual solution tells us that if we increase remember, the first constraint was on the number of. Remember, the first constraint was on the number of man hours. We had 60 man hours available, 75 machine hours available, and 84 units of wood. Now, the dual solution tells us that for every hour we increase the number of man hours, we'll get an increase in $18 1/3 profit. For every hour of machine time we increase, we'll get 0 increase in the profit, and for every extra unit of wood we throw in, we'll get a $3 1/3 profit. The reason there's no increase in profit, there's no additional profit by increasing the number of machine hours, is in our final solution we aren't using all the machine hours we have. So looking at the dual solution tells you how you could further increase your profits by changing your resource limits. And in fact, we actually tried resolving the original problem with 85 units of wood available instead of 84, and the optimal profit did increase by exactly $3 1/3. this is useful because it may be easy to change your resource limits. You know, it's easy to change the number of machine hours, man hours, or wood that you have available, and this dual solution tells you how much that will help you.